On HP Museum, you can find an article number 700, which is a benchmark maintained by HHC. And in this article, you can find some source code for about every calculator, and particularly the RPN calculators. The benchmark is around the n-queens problem. You can go to the site to see the article. You will have a lot of information. And it happens that the programs for RPN calculators have, how to say, are full of interesting features, Microsoft speaking. So, there is a sample code source for the basic language. If you look carefully, you will see that there is a lot of array access in the code, and line 110 is the inner loop. In the inner loop, you have two array access. The problem is that the first array access is the same on every step of the loop. This is nothing in BASIC, but we will see later why it is important. In C language, it's mainly the same thing, but the main difference is that a C compiler sees that this array access is a constant inside the inner loop, and he moves it outside the loop. There is another source code for something like C, which I don't know, but if you look carefully, this is not an array access. This is a variable, and all the code is changed to avoid this array access. So this code is optimized and is more efficient than this one. So at the beginning, the benchmark is based on this code, which is the non-optimized code. And if you go further, you see that the RPN programs are following the basic source code. The problem is that there is a double array access in the inner loop, and if you take a 15C plus, which use an index to access to arrays, the inner loop keeps reloading the index for the two array access. It's used for the runtime. So the goal is to avoid as many array access as possible. So it's happened that the source code for the 15C is a very good sample of what should not be done. I know it's a joke. What I will show you can be applied to about every other programs in this benchmark. So, in the source code you find this code. It happens that the 15C plus and 15C can do arithmetic with RCN. Usually you find arithmetic with store this is the efficient code. Problem. In the source code for the 15C, you find this code, which can be replaced with this code. No comments? I think.
Yep.
I can't stay that close to the edge of the table. You're just going to knock it on the floor again.
No, it was on my pocket.
Okay.
Then there is another case. In this case, they subtract one from a register, then you recall the register to see if 0. In fact, you want to jump only if the value is not 0. You can put this code, which will be more efficient. And this is the same case for the HP-41 in the same benchmark. They use this with a dummy
Degree.
no, an up instruction to recall the value and do their test. You can change the code with this code, which will be more efficient. Then we have about the same thing. Here is where we are counting the number of queens that we try to put on the checker. I just move it in a place where the next instruction, no matter if we skip this instruction.
Wow.
So this way, this code is more efficient than this one. And in this part, you can see that we are loading 2 times the same. We are loading 2 values, and we are reloading 2 values which are the same. Why not use these values on first time and avoid reloading? This is what I have done with using some swap, and I do my subtraction here. It was there. So this code is shorter than this one. And now, if I applied the optimization found in this program, it changed completely the program for the 15C, and this is optimized for about everywhere it can be, and the result is this.
Whoa. Pretty good. Patrice, is that the benchmark from the museum? The N
This
N
is
Queens?
the benchmark of the original program.
Degree.
This is the benchmark of the program found here for same result. We save 1/3 of the runtime. So we have seen a lot of features which should not be done in a program like that for a benchmark. I think so. Yes?
What about the, I mean, there's dozens and dozens of source codes in that article.
Sorry?
There's there are dozens and dozens of source codes for various machines in that article for the 8 queens problem. Do they all make the same sort of suboptimal choices? I mean, could they all be improved? It seems to me that If they're all got the same flaws, they're still valid as benchmarks.
If you want your calculator to have a better place in the benchmark, you have to provide a source code more efficient than the one already provided to the access, since about every programs were given by forum members.
So we'll let the Casio people optimize their code and the TI people optimize their code, and we'll just fix our.
So all I can say, optimize the program for your calculator and provide it to the access, and I think it will update its benchmark. If we all do one calculator RPL, we can have all the HP calculators improving their position in the benchmark.
As well as it should be.
But we can go even further, because the NP problems come in two flavors to solve the problem. You have the flavor which is used in the benchmark, and you have to study a little to see how it works. But when you try to place a queen somewhere on the checker, you have to check all the previous queens every time to see if you can or not put a queen in a cell that you want. But there is another flavor to solve the problem. It's using a bitmap. To use a bitmap, you have to use a functionality that's found mainly in microprocessors, and microprocessors is the specialty of the 16C. If you see this, with the bitmap algorithm, you have three values. Each of these values are telling you which cell are located by a queen, and those three values are your three values are showing the cells vertically and for the two diagonals which are under every queen. So in this value, you see that you have two queens locking two cells with one diagonal. Here you see that you have two queens locking two cells with the other diagonal. And there you see that you have three queens locking three cells for the next line. Here I am putting a new queen in the third cell. So the technique to go from these three values to these three new values, I transfer the position of the queen in a binary value, which is the third cell. I do a logical operation which is OR, and you see that the one there is going here. We are merging these two values in this one. We do the same here, and the same here. Now, to take into account that we have diagonals, I have to shift the two values for the diagonals. This one, you see the ones are moving to the left, and the ones are moving to the right. And at the end, I have three new values, each showing which queen, which cells for the next line are locked by queens. the main interest of this thing is that if I OR the three values, I obtain a new value, which is the synthesis of the three values here, and I see that there is only two cells available for the next line. Why is it interesting? This value tells me that a queen is possible or not in a cell by only testing one bit. And I don't have to look to the previous screen, because this value is the synthesis of all the previous screen already on the board. This is how the three values are evolved. In first, I put the queen in cell number 8. You see that on the next line, this queen is locking this cell, and this one. So for every queen you see that the left diagonal is locking some cells. Here you see the right diagonal. Here you see the vertical locking. And here you see the synthesis of every line, which is this, and this. This is the inner loop of the original program for the 16C. This is the inner loop for the new program of the 16C, because only one bit to test tell me if I can put a queen or not on a cell. You know these two short? This is the result of the bitmap technique. Any questions?